Okay, I'll get started. Hope you can hear me clearly. Today we're going to be moving on to a new topic. We talked about electricity and electrical interactions and the laws of nature that describe electrical interactions. We talked about magnetism, magnetic interactions, and the laws of nature that describe magnetic interactions. And in today's class, we're going to move on to a topic that's called induction. It's called electromagnetic induction. And it really was the bridge between electricity and magnetism, those two forces that we've talked about. It was the bridge that joined together electricity and magnetism into what we call electromagnetism, right? A single word that combines those two forces, electricity and magnetism, into a unified force, single force we call electromagnetism. So this is a sort of big topic. It was an important topic. So today's content, the items I'd like to go through are the following. I've listed three here. Firstly, we're going to look at how electrical potentials, electrical currents are actually generated or actually caused or actually produced by time-varying magnetic fields, by time-changing magnetic fields. This is a completely new phenomenon effect. Then we're going to move on to a law of nature that describes this completely new effect. And to write down that law, we're first going to talk about magnetic flux, what that is, and then we're going to write down Faraday's law for electromagnetic induction, see what that is. And so that's the basic plan for today, those three topics. Just to give you a little perspective, I love to do this. Whether it is a real perspective or not, I don't know. But, you know, electricity and magnetism, they go back thousands of years to antiquity. You know, the first hints, the first observations of electricity and magnetism go back more than 2,000 years. The topic for today's class, topic of induction or electromagnetic induction, the first hints, the first suggestions of electromagnetic induction, much more recent, less than 200 years ago, and due to a famous scientist, Michael Faraday, who we've actually talked about before. So this is much more modern physics. You might wonder, this is not a donut that keeps appearing in my overheads. This is not, I didn't go to McGee's or Dunkin' Donuts and take a picture of a donut. This is a coil of wire, many turns of wire. And it's a historic coil of wire because it's Michael Faraday's coil of wire that he discovered induction, electromagnetic induction with. So that's why I'm using this picture. It's not that I like donuts. I mean, I like donuts, but that's not the reason. Okay, this is a really great picture too that nicely illustrates electromagnetic induction, nicely illustrates this sort of new phenomena in electricity and magnetism. In this picture, let me get the pen going. These lights are fluorescent lights, like you might have in a, I don't know, in a office or in a kitchen or something like that. They're fluorescent lights. The interesting thing about this array of fluorescent lights is that they are not connected to power. there's no wires coming out at the top and bottom of these fluorescent lights that are plugged into a power supply. But despite the fact they're not connected to power, connected to a power supply, these fluorescent lights are lit. So why are they lit? They are lit because of induction, because of electromagnetic induction. Above the wires, you might have spotted it. Here's one. Here's another one. Here's another one. And here's another one. I could go on. Are power lines. Now, those power lines contain electrical currents, large electrical currents. And those electrical currents are actually alternating currents, meaning they flow to and fro rapidly. And so those electromagnetic currents create a magnetic field. And because they're alternating electrical currents, they create a magnetic field that's alternating to and fro rapidly. And so they're creating an environment around a power line of alternating magnetic fields, alternating B fields. And what you're seeing is that alternating, time-varying, time-changing magnetic fields induce electrical potentials, electrical currents that are lighting the lamps, that are lighting the lights. And so it's a powerful demonstration. These lights are not, as I say here, not connected to a physical power supply, but rather they're being lit by the phenomena of induction. They're being lit by being immersed in a time-varying, time-changing magnetic field. It's an incredible effect. Okay, so I just wanted to mention this sort of shout out to two of the heroes of induction. One of them is Michael Faraday. I love this guy. And another one is an American scientist called Henry. So let me just mention these two scientists. So Michael Faraday, who was, around a couple of 100 years ago, was the first to discover and publish the new phenomena of induction, electromagnetic induction. So he's credited with the discovery of it. He's a very interesting scientist because he had no formal training, no real mathematical training, but he made these immense contributions to science. And in many ways, through induction, is responsible for our modern lifestyles. Induction really is the birth of our modern lifestyles. Joseph Henry is the other scientist I wanted to point out. And my pen has fallen on the floor, so I'm going to head underneath my desk right now, but I am coming back. So he was an American scientist. He just missed being the first person to discover induction. He was just behind, sort of months behind Faraday in discovering induction. But he actually went on to develop a lot of the applications, the modern applications of induction. So again, he's really responsible for much of our modern lifestyles are based on this effect of induction. Okay, so I got a couple of slides here, a few slides actually, to show you an example of induction. And then we'll look at a couple of videos I made, demonstrations of induction. And then that'll lead us into this topic of the laws of nature for induction. Okay, so this is, imagine these next few slides, you've gone back in time, you're with Michael Faraday or you're with Joseph Henry, and you're working in their labs and trying to discover induction. They were looking for a really strange effect, a really weird effect. They were looking for electrical signals that were produced by the influence of magnets, bar magnets. And right now we think of electrical signals and electricity as something separate from bar magnets and magnetism. So it was weird that they were looking for a connection between the world of electricity and the world of magnetism. So this is over here on the left-hand side. This is a kind of sketch of the modern day version of the experiments that they were doing. So if you look in this sketch, here I am, I'm holding a magnet. And as we know, the magnet has a north pole and a south pole. And the magnet has field lines that emerge from the north pole, and they ultimately return to the south pole. And then in addition to the magnet, I've got a current loop here. I've got a looper wire here that's connected to a, we might call it a galvanometer or a voltmeter, a device to measure voltage differences or potential differences. And in this sketch, in this picture, I'm imagining I'm holding the magnet in the neighborhood of the looper wire. And I'm asking, do I see some influence of the magnet on the looper wire? And do I see some electrical potential difference in the looper wire caused by the neighboring magnet? And the answer is no. There's no electrical potential difference between the terminals of the looper wire when that magnet is in the neighborhood of the looper wire. And so they were kind of looking for this type of effect, the influence of a magnet on a on this looper wire. Now, what they did notice was really interesting. What they noticed was that when they brought up the magnet to the looper wire, so in the last slide, we had the magnet sitting on the desk, say, near the looper wire. But of course, you had to put the magnet close to the looper wire. And then after you've looked at the results, you might take the magnet away from the looper wire. And what they noticed was influences of the magnet when they put the magnet close to the wire, and influence of the magnet when they took the magnet away. So there's no influence when the magnet was packed away. There was no influence when the magnet was just sitting nearby the looper wire, but there was actually an influence of the magnet on the looper wire when they brought it close to or removed it far from the looper wire. And so in this sketch here on the left, you're seeing the case of when we bring up the magnet. So I had it in my desk drawer and I take it out and I bring it up to the looper wire. And so I'm trying to show here with this little arrow, this is the moment, this is this sort of fleeting moment when I'm bringing the magnet up to the looper wire and I'm exposing the looper wire to the magnetic field of the magnet. And in that moment, that short-lived moment, right, there's a potential difference across the terminals of the looper wire. And that turned out to be the discovery of induction. It turned out to be this huge discovery for our modern lives. Oh, sorry. Okay, this is meant to be, I got this messed up slightly. This is meant to be when I'm pulling, I'll change this on my slides. It's getting me flustered now. This is when I'm meant to be pulling the magnet away from the looper wire. So putting it back in my desk drawer. And they noticed then also, when they moved the magnet away, like when they moved the magnet close by, they saw an electrical signal in the looper wire. Now, if we went back to the prior slide, the signal that I saw was -1 volt. And when you take the magnet away, the signal that we're seeing here is +1 volt. So bring the magnet up, you get an electrical signal, electrical potential, electrical current. Taking the magnet away, you get electrical signal, electrical potential, electrical current. The signs, the directions of the potential and the current are opposite when you bring the magnet up and when you take the magnet away. They saw that. Okay, let me show you a couple of demonstrations, a few demonstrations of this effect, because it's quite startling, I think. So I think you can see my my Canvas page here, and I've got a video. And in this video, if I get this mouse going, there's a few things. I'm going to point these out so that there's a loop of wire. It's down at the bottom here. You can't see the entire loop. And it's connected to a voltmeter here. And then there's a magnet over here. And in Faraday's experiment, we pictured Faraday bringing up a magnet to the loop of wire. In this case, I'm actually going to do the reverse. I'm going to bring up the loop of wire to the magnet, but it's very much like Faraday's experiment. So I think I'm going to show you here that it is a loop of wire. It's just a single loop of wire attached to the voltmeter, like in Faraday's experiment. And I'm going to grab hold of a section of that wire. I think I'm doing that here. Nice stretched section of wire. And I'm going to put it into the magnet, pull it out of the magnet. And watch the needle as I do that. As I push it in, the needle deflects one way. As I pull it out, the needle deflects the other way. Push it in, deflects to the right. Pull it out, it deflects to the left. That's exactly like Faraday's experiment. That is an incredible phenomenon, incredible effect. And as I say, and we'll learn this in the next class, it's the heart of our modern lifestyle. So we should thank Faraday and thank Henry for that. I want to show you another one. Okay, this one is going to be even closer to what Faraday and Joseph did in those slides I just showed. So in this little video, I've got a loop of wire. Now, it's a little more complicated loop of wire. So you see the terminals here of the wire on the left and on the right. And this is many, many turns of wire. So this is kind of like our version of Faraday's coil. There's hundreds, probably thousands of turns of wire in here. And its terminals are connected to this voltmeter. And I'm going to, like Faraday, like Henry, bring up a bar magnet to this loop of wire, this many-turned loop of wire. So let's see what happens here. So I'm proving to you that, look, this wire on the right goes to the right-hand terminal of the coil. This wire on the left goes to the left-hand terminal of the wire, and there's many turns of wire. And here's the voltmeter. It's reading 0 right now. And then I'm going to bring up a bar magnet. It's one of these regular old bar magnets. There's the red end, the North Pole, and white end, the South Pole. And I'm going to, I think I take the red end here. I'm going to take the North Pole and I'm going to stick it into the bar magnet. Look at it deflect to the right. And then if I pull it out, it deflects to the left. And I'll do it again. Push it in, deflects to the right, pull it out, and it's going to deflect to the left. That's exactly what Faraday Henry did. Now I'm putting the South Pole in. and it deflected to the left first. And when it pulled out, it deflected to the right. Push it in, deflects to the left, and pull it out, it deflects to the right. So the south poles and north poles both cause opposite deflections when you push in versus pull out, but they themselves have opposite deflections. Got one more. Got carried away with this. Now, this one's a little bit different in a way, but in its heart, its core, it's actually very similar. And so that's why I'm showing you this other video, because you might at first think, well, this looks like a very different effect. But if you think about it in the right way, it's a very, very similar effect. So in this video, I've actually got here in the center, in the foreground, there's actually two solenoids. Now, one is sitting inside the other. So you see the outer solenoid. That's what you see with the copper wires there. But inside that, I'll show you, there's another one, a smaller solenoid. The smaller solenoid is connected through a switch to this power supply. And I can switch it on and switch it off. I can turn that solenoid on and off. I can turn its magnetic field on and off, and I'm going to do that. The larger solenoid, the outer one, that's just connected to this voltmeter, which is wires that lead to the voltmeter. And we see 0 volts right now. So let's watch this video. And I'm going to take out that smaller solenoid here, you see? So there was a solenoid in there. It's not connected to the other solenoid in any way, physically. And the leads on that solenoid one goes through a switch to the power supply, and one goes directly to the power supply. So that's the smaller solenoid, and then here's the larger solenoid that I'm going to put it in. It's, again, also many turns of wire, and it's got a black and a red lead, and they're just connected to the terminals of the solenoid and then connected to the galvanometer or the voltmeter. So I'm going to put the little package of solenoids back together, the small one inside the large one, switch on the power supply, and then I'm going to start actually switching on the smaller solenoid. Right now there's a switch, but it's open. And watch the needle when I close it. I mean, wham, that's a big signal. At the moment I close the switch. And another big signal the moment I open the switch. Now that signal's only present when I close and only present when I open. When the solenoid, the smaller solenoid, is not energized and just sitting there, there's no signal. Actually, when it's energized and just sitting there, there's no signal. It's just when I switch it on or switch it off, at those moments, we get a signal. Okay, so that's great. So good, I've forgotten what I'm going to do next. I'm going to go back to the slides. Oh, and Lady Gaga's come to class because this is such an important topic for our modern lifestyles. So in each of those experiments in the videos, there was a common theme. So, you know, if you think about the experiments, since the first couple of videos, we were moving around magnets or we were moving around wires. In the last video, we were switching on what we call an electromagnet, a solenoid, and we were switching off an electromagnet, a solenoid. The common thing is that what we were doing by moving magnets to and fro or switching on and off electromagnets was changing magnetic fields. And those changing magnetic fields are what induced the currents, what induced the potentials. And it's those changing magnetic fields that cause induction, that are induction, and cause these currents and cause these induced voltages. I just see a question in chat now. What's the difference between positive and negative EMF? How do we predict the sign when moving a magnet towards or away from an electrical source? Yeah, so let me say something about the first part of that question. So in all of these experiments, we induce a electromotive force, or we induce a electrical potential difference. And we induce an electrical current. We induce a flow of electrical charges. Both those things, the potential and the current, have a sense to them or a direction to them, right? The current can flow one way or the other way around the circuit. The electrical potential can have one end of the loop more positive potential than the other end, or one end more negative than the other end. So both the current that we generate and the potential that we generate has a sense or a direction or an orientation. And so that's what I mean by, positive, negative potentials or positive and negative EMFs, and what we mean by, currents that would be positive or negative, or clockwise or counterclockwise. Now, the second part of this question is, how do you know which orientation you're going to get? How do you know which sense you're going to get? And we're going to come to that later in the class. I won't answer that now because we need to learn some new things to be able to answer that. But you can predict which direction the needle swings when you push the magnet in or pull the magnet out, or when you switch the solenoid on or switch the solenoid off. You can predict it. We will predict it. Okay, so now I want to move on to building a law of nature that describes this effect of induction. And to build the law of nature for the effect of induction, we've asked to first talk about a new topic, which is magnetic flux. It's rather analogous to electrical flux we met before. So that's why I took this slide from an earlier class. It's a reminder of electrical flux. And I'm just getting the pen going here again. So if you remember, when we're talking about electrical interactions, we talked about both fields and fluxes. They're both related to one another. When you think about field, you tend to think about the field at a specific point. When you think about flux, you tend to think about the electric flux through a particular surface. So it's kind of a different way of thinking about fields and fluxes, with points in space and surfaces in space. But we wrote down an equation, and we kind of pictured the relationship between flux and field. So in this equation, right, here's the electric flux. We gave it a symbol phi, and here is the electrical field. And the electrical flux of an electrical field through a particular surface is, if the field is constant, uniform, is simply the area of the surface times the perpendicular component of the field. That's this equation here. Or we can write it slightly differently. It's the electrical field strength times the area of the surface times the cosine of the angle between the vector representing the electrical field and the vector representing the surface area. So that was the second way of writing it. So this was our definition of electrical flux. If we wanted to define it in words, we would said that the flux through a surface is in proportion to the number of field lines that are passing through the surface. So a small flux through a surface would have very few field lines passing through the surface. A large flux through a surface would have a lot of field lines passing through the surface. Well, that was electrical flux, but magnetic flux is the same, except it's related to magnetic fields rather than electrical fields. And so this slide summarizes our definition of magnetic flux. And it's the same equation that relates the magnetic flux, given the symbol phi, to the magnetic field here, the symbol B. And it's the same sketch, right, that relates the flux through this rectangular surface to the field in the neighborhood of the rectangular surface. And likewise, again, when you think about magnetic fields, you tend to think about the fields at a point in space. When you think about magnetic fluxes, you're thinking about a surface and the flux passing through that surface. And the magnetic flux through a given surface, particular surface, is one way of thinking of the magnetic flux here, is that it's the area of the surface times the component of the magnetic field that's perpendicular to the surface. That's this style of writing it. Or you can think of it as the strength of the magnetic field at the surface times the area of the surface times the cosine of the angle theta. That's the angle between this vector that represents the magnetic field and this vector that represents the surface. And again, if you want to think more qualitatively about magnetic flux, the flux through a surface is in proportion to the number of magnetic field lines that cut through the surface. So if you have a lot of field lines passing through a surface, then that's a large magnetic flux. If you have a small number of field lines through a surface, then that's a small magnetic flux. Let me just show this slide and the next slide quickly, that just to illustrate some of the features of that relationship between flux and field and surface that we first met for electrical fluxes, and now we're meeting for magnetic fluxes. So look, in this example, I got a surface here. This one on the left, 1 square meter. Oh, I've jumped a slide, I think. Let me get back. Yeah, I got one surface here, over here on the left, 1 square meter. I got one surface in the center, 1 square meter, and I got one surface over here on the right, 1 square meter. They're all the same surfaces, but they're immersed in different magnetic fields. So perpendicular to the surface on the left is a strong 15 Tesla magnetic field. Perpendicular to the surface in the middle is a moderate 10 Tesla magnetic field. And perpendicular to the surface on the right is a weaker 5 Tesla magnetic field. Now, in each case, the flux through the surfaces is the product of the perpendicular component of the field, B, times the area of the surfaces, A. In this case, it's a simple geometry, right, where the field lines are perpendicular to the surface. That means that the field vector and area vector are actually parallel one another. So the fluxes in these cases are just strength of the field times area of the surface, strength of the field times area of the surface, strength of the field times area of the surface. All the areas are the same. They're all 1 square meter. The fields, the 3 fields are different. They're largest over here on the left, 15 Tesla, smallest over here on the right, 5 Tesla. And so if you calculate the fluxes, these are the 3 fluxes through those 3 surfaces, 15, 10, and 5 Teslas meters squared. And that flux is an important number, so we'll give it the units Webers. This WB is a Weber, and so that's a unit. So that's one example one illustration of this relationship between flux and field. These two quantities that we use to help us understand magnetic interactions, and also induction effects, electromagnetic induction. Here's a second slide that illustrates the relationship between field and flux. And this one illustrates how the flux depends on the orientation of the surface in the field. So in this particular case, I've again got three same size surfaces, 1 square meter on the left, 1 square meter in the center, and 1 square meter in the right. This time they're all immersed in the same strength field, 50 Teslas. There's 50 Teslas on the left, 50 Teslas in the center, 50 Teslas in the right. The field lines are equally packed on the left, center, and right, indicating that the field strength is equal sized on the left, center, and right. The field lines all go left to right on the left, center, and right. So the field is the same direction everywhere too. The only thing that's different for the three fields, for the three surfaces, is the orientations of those surfaces in the magnetic fields. So over here on the left, the vector A representing the surface and the vector B representing the field, they're in the same direction. So theta in the definition of flux would be 0 degrees. Over here in the center, well, the vector representing the surface, that vector's pointing down. The vectors representing the field, that vector would be to the right. And so they're at 90 degrees one another, the vector A and the vector B. And so theta in the equation for the flux, that's 90 degrees here. And then in this situation on the far right, we're somewhere in between these extremes, okay? The field lines aren't perpendicular to the surface. They're not in the plane of the surface. The vectors A and B aren't parallel or perpendicular. There's actually an angle in this case of 30 degrees. Theta is 30 degrees for the angle between A and B. And those three different orientations cause three different fluxes through these three different orientations. So when I come to calculate the flux of the magnetic field through the surface on the right, on the left, then it's the flux is the strength of the field times the area of the surface times the cosine of the angle between the A and B vectors. That cosine of angle is 0 degrees. Cosine of 0 degrees is 1. So this is 1. And so we just get 50 Teslas times 1 square meter times 1. We get 50 Webers as the flux. In the center here, same formula to calculate the flux, strength of the field, B, times the area of the surface, A, times the cosine of the angle between the vector A representing the surface and the vector B representing the field. Here that cosine is 90 degrees. Cosine of 90 degrees is 0. And so although there is field, although there is a surface, there is no flux in this case, 0 Webers of flux through that surface. And then finally over here on the right, this is where we had a surface that was orientated somewhere between being parallel and perpendicular to the field lines. Again, the same equation for the flux, phi, is the strength of the field times the area of the surface times the cosine of the angle between the vector A representing the surface and the vector B representing the field. The cosine of 30 degrees, if I remember that right, that's this famous one, it's square root of 3/4. And that flux comes out to be 43 Webers. So that's an illustration. The last slide was an illustration of how the flux depends on the field strength. This is an illustration of how the flux depends on the orientation of the surface. Okay, so that's introducing magnetic flux. It was fairly easy to introduce it, I thought, for me, not because I'm any good at explaining magnetic flux, but because I'd already gone through the business of explaining electrical flux. And magnetic flux is the magnetic equivalent of electrical flux. So that made it easy. Here's a nice little example of magnetic flux. So as you probably recall, the Earth, here's a picture of the Earth. Well, not a picture of the Earth, a sketch of the Earth. The Earth is a magnet. And just to confuse everybody, right now, the magnetic North Pole is at or close to the geographic South Pole. So this is actually the down here is the North Pole of the Earth, magnetic North Pole of the Earth. And the magnetic South Pole is close to the Arctic, the North Pole, geographic North Pole. So the South Pole is up here. That's why you see the field lines coming out the bottom of the Earth and heading back into the top of the Earth. If the Earth does have a bottom and a top. Of course, that's a totally biased perspective as somebody that lives in the Northern Hemisphere. Okay, so what does this question say? It says, Argentina has a greater area than Greenland's area. So if you think about those two countries, Argentina in square miles or square kilometers is greater in area than Greenland. But, okay, so supposing you're from Greenland and you're feeling a bit disappointed that you're smaller than Argentina. Greenland has a larger magnetic flux through Greenland's surface than Argentina has magnetic flux through its surface. So Greenland wins the magnetic flux. Argentina won the area. Why is that? Well, here's the reason. So Greenland is closer to the magnetic North Pole than Greenland is closer to a magnetic pole. It's actually the South Pole. Then Argentina is closer to a magnetic pole. So I had said that the North and South poles were kind of reversed from the geographic North and South poles, but I'm just worrying about how closely you are to a pole, whether it's a North or South pole. I'd also, I think, mention that the geographic and magnetic North and South poles, their axis isn't quite aligned. So if you're at the geographic North and South poles, you're not at exactly magnetic North and South poles and vice versa. Well, it turns out that Greenland's very close to a magnetic pole and Argentina's less close to a magnetic pole. If you're in a country that's close to a magnetic pole, the magnetic field lines are coming out of the ground vertically upwards, or they're going into the ground vertically downwards. If you're in a country that's far from the poles, then the magnetic field lines of the Earth may be going almost horizontally. They're not coming out of the ground, sprouting out of the ground or diving into the ground. They may be going, horizontally across your country. And that's sort of, it's a bit extreme of what Argentina and Greenland are, but it's the reason that Greenland has much more flux because the flux is sprouting out of the ground, whereas Argentina has less flux through its surface because the field lines are just shooting across the surface. Anyway, I kind of like that question. Okay, now let's move on to the law of induction. We better get there. I've spent 45 minutes to get there. So we better talk about the law of induction. It's called Faraday's law because, of course, Faraday was the is credited with discovering induction. And here's Faraday's law. It's right upstairs here. It's in a sense a really simple law, although it can be sometimes a little challenging to apply it. So let's talk about this law. The law says the following. It says that induced EMF in a loop of wire is in proportion to the negative time rate of change of the magnetic flux through the loop of wire. This is the induced EMF in the wire. So this is the potential difference that's created in the wire. This is the number of volts across the terminals of the loop of wire. And this is that mouthful, the negative time rate of change of the magnetic flux. So look, you see magnetic flux, that's the phi. You see it's the change of flux, that's the delta phi. You see the rate at which it's changing over the time, that's the delta phi over delta t. And you see it's the negative time rate of change because of the minus sign here. So this mouthful, negative time rate of change, equals induced EMF, is this equation here. So the equation is just a handy way of recalling that concept, idea, law that the induced EMF is determined by the time rate of change of the negative time rate of change of the magnetic flux. Just as an example, I put down a little example here. Supposing, and this is an example related to sticking the bar magnet into the neighborhood of the coil. So supposing the flux was initially 0, no magnetic flux through the coil. We stick the bar magnet close to the coil, we get 0.02 Webers of flux through the coil. And we did that in half a second. What's the induced EMF? We had no field, we have a field. We had no flux, then we have 0.02 Webers flux. And we achieved that change in half a second. So what's the induced EMF? Well, simple application of Faraday's law of induction. It's the induced EMF is the negative time rate of change of the magnetic flux. The magnetic flux changed by 0.02 Webers. The time interval was 0.2 seconds. The rate of change of the flux was 0.04 Webers per second. The negative time rate of change is a voltage that is minus 0.04 volts. And that's the signal. Look, that's the signal we see in the voltmeter, in the galvanometer. So that's the law of induction. The same law applies when you pull the magnet out. So this is the same slide, but now I'm pulling the magnet away from the bar magnet. If you look at the motion, it's away from the bar. I'm pulling the bar magnet away from the coil rather than pushing the bar magnet towards the coil. We can again apply Faraday's law of induction, that the induced EMF is the negative time rate of change of the magnetic flux. We're pulling the magnet away, so again, we got a change in flux. We originally had a flux that was the initial flux, 0.02 Webers. When we take the magnet away, I put it in my desk drawer, the flux is now, from the magnet, it's gone away. There's 0 flux. And I pulled it away as fast as I pushed it towards the magnet, pulled it away in half a second. So that's a change in magnetic flux that just occurred, and we're going to get a signal. We're going to get induction. We're going to get induced EMF, induced current. And here I am calculating that induced EMF with Faraday's law of induction. Faraday's law of induction says that the EMF is the time rate of change of the negative flux, negative time rate of change of the flux. The flux this time changed by minus 0.2 Webers because it went down from 0.2 Webers to 0. That change occurred in half a second. So the time rate of change is minus 0.04 Webers per second. And that gives a induced EMF from the negative time rate of change that is plus 0.4 volts. And look, that's what we're measuring over here. So it's a second application of Faraday's law. Okay, got a quiz question. Okay, I think time is up. So let me just go through the answer for this quiz question. It looks like a lot of you got this completely correct. So a circular loop of wire in a uniform magnetic field with its plane, the surface formed by the loop, perpendicular to the field lines. So that's the geometry. And then shown in the sketch is also kind of a horizontal axis, that's the black horizontal arrow, and a vertical axis, that's the vertical arrow. And we're asked which of the following scenarios does not cause an induced current? Well, induced currents are caused when you've got a changing flux through the loop. So not causing an induced current is when you don't have a changing flux through the loop. You don't have a changing flux through the loop if we just imagine I grab that loop and I just slide it left to right or right to left. If I just slide it along that horizontal axis, the same number of field lines are going through the loop. So the flux through the loop is unchanged, and so there is no induced EMF, no induced current. If I was to do the other things to it, like supposing I crush it, right? Feeling destructive, I'm tired of that loop, I'm going to crush it. Well, now, if I crushed it down, there's not as many field lines passing through it. And so I will have had an induced EMF. If I rotate it about the vertical axis, as you rotate it, you'll get more or less field lines going through the loop. And so you get an induced EMF. And if you turn off the field, for example, well, that's certainly going to change the flux through the loop. It's going to go away. You'll get an induced EMF there too. Okay. So last thing I want to talk about is, before we maybe do another example or so, is what we call Lenz's law. This is an interesting little thing, actually. Within Faraday's law is Faraday's law again, this whole thing. Induced EMF is the negative time rate of change of the magnetic flux. The negative bit, that minus sign, is called Lenz's law. I don't know how this happens. So I don't really know a lot about Lenz. I was going to try and Google him, but I don't know a lot about Lenz, to be honest with you. I don't know if he was like a buddy of Faraday. And, you know, Faraday came up with his law that the EMF is the negative time rate of change of the magnetic flux. And Lenz said, well, you know, Faraday, that's a great law. Can you let me have the minus sign? So I don't know if it's like that, or probably Lenz did make big contributions to Mohammed's question of, you know, what sense is the current going to flow in when you induce the current? What direction, orientation is the potential going to be in when you induce a potential? So he must have made a big contribution there. And his law is the following. He says that the induced current flows, the direction of the induced current, it flows to create a what we call an induced field. It's a kind of a new field that wasn't originally there. It's an induced field that's created by induction. Creates an induced field that's opposite the change in the field that's happening by bringing the magnet up or pulling the magnet away. So this is an important point that we have to thank Lenz for, that when you get induction, there's kind of this original magnetic field at the bar magnet, and you brought it up to the coil or you took it away from the coil. There's the magnetic field of the solenoid that you switched on or you switched off. So that's the magnetic field that's causing the induction. That's the source of the magnetic flux that's causing the induction. But at that moment that there's induced currents, induced EMFs, there's actually a second magnetic field, an induced magnetic field that's caused by that induced current itself. That's going to create a magnetic field. And Lenz's law is that that momentary, that fleeting, that instantaneous induced magnetic field is always in a direction. It always has an orientation that is opposing or is opposite to the change in the original magnetic field. So as an illustration of that, take a look at this picture here. So this is the case where I'm bringing the magnet up to the coil. And so if you're the coil, if I'm the coil, I'm suddenly seeing a magnetic field that goes from right to left appear inside my windings. That induces induced EMF, induces an induced current. That current will flow in such a way that it creates a magnetic field that opposes that change. So it's going to create a magnetic field here, induced magnetic field that's towards the right, because the field towards the right is opposing the magnetic field that has just occurred when I brought up the magnet, which is towards the left. So you see this magnetic field is opposing the change. And to create that magnetic field, this is where you take your right-hand rule for a coil, a loop of wire. This is the biggest reason we learned that particular right-hand rule. You point your thumb in the direction of the induced magnetic field. So if I would recommend trying this now. Take a look at this slide. You can see the direction of the induced magnetic field in this slide. It's that magenta arrow that's opposing the original magnetic field, the change in original magnetic field. Point your thumb in the direction of the induced field. So that's your thumb's going, of the right hand is going towards the right. Then the fingers curl in the direction of the current, so that they're going to come out of the top of this loop. They're coming out at the top and they're heading in at the bottom. That's how my fingers are curling, at least. And so that's how you figure the direction of the induced current. And it's how you can figure the orientation of the EMF. It's going to cause a current that flows in that direction. So that was Mohammed's original question. Let me show you a second example of that. Okay, do you notice what happened then? I went from pushing the magnet in to taking the magnet away. I got a mistake on this slide. Oh gosh, that's not a good mistake. Some mistakes you can get away with, but let me be careful about pointing this one out. This was because I was cut and pasting these slides. I always, cut and pasting slides, right? You think you're saving time, but there's a danger when you cut and paste. And here's the danger. So let me explain the mistake on this slide. I want to show it to you. So this is when I pushed the magnet in and I got an induced field that opposed the change. Now I'm pulling the magnet out, so I'm taking away this magnetic field that goes to the right. The induced field, let's see if I can get a magenta. The induced field is going to be this way, because it's going to try and replace that original magnetic field that's gone away. I hope that's okay. So I'll correct this in the slides, but that arrow, I didn't flip the arrow, the direction of the arrow for the induced field. So now we want to create a field to replace the original field when I take the magnet away. And so I've got to make a field that goes towards the left now. And so again, if you get your right hand, point your thumb towards the left, the current's got to curl this direction. Because I got the field wrong, I got the current wrong. The current's going to go this way. It's going to come out at the bottom of the loop and go in at the top. So that's the direction of the current in this case. And so this is how you figure out the orientation of the potential difference in the direction of the current. Here's a second example. Let's pray to Lenz and Faraday got this one right. A second example of Lenz's law for the direction of the induced currents and induced EMFs. So let's take a look at this slide. Let's take a look down here. It's quite a busy slide, so I just want to go through some details of it. I got a solenoid. Look at this solenoid here. And then I got a coil of wire, or a loop of wire in the neighborhood of the solenoid, just on the right of the solenoid. And I'm picturing that situation 3 times. Okay, so it's in each of these 3 pictures, it's the same solenoid and it's the same loop of wire. And in each of these 3 pictures, I'm not moving the solenoid or the loop of wire around. They're always in the same position. What I am doing, look, the solenoid is connected to a battery and a switch. And originally, the switch was open, so the solenoid was off. There's no magnetic fields, there's no induced EMFs, no induced currents. But then what I'm going to do, as I go to picture number 2 in the center, I'm going to switch the magnet on. And then as I go to picture number 3, I'm going to switch the magnet off. And so that's what I'm doing on this slide. I've built this setup of the solenoid, the coil, and the circuit. I energized the solenoid in sketch 2. I de-energized the solenoid in sketch 3. And I'm going to ask the question about, well, when at that moment I energize, what's the induced current, and specifically the direction? And when I de-energize the solenoid, what's the induced current, and specifically the direction? So I'm going to try and answer these two questions. So we're going to do that with with Lenz's law. So look, when I switch on, so I'm thinking about the center sketch here, switching on the electromagnet, suddenly I create a magnetic field around the solenoid that the field lines would come out of the North Pole and they would streak into the South Pole. So I created a field here by switching on the solenoid where the field lines pass from right to left. through the coil of wire. So what's going to be, think about what's going to be the induced, at that moment, the induced magnetic field. If we switched on a field that goes from right to left, the induced magnetic field is going to be from left to right. It's going to oppose the change. So the induced field, if I can draw it, B induced, is left to right here, opposing the change. Now, that tells you the direction of the induced current. Again, take your right hand. Here's my right hand. And I'm going to put it next to the slide, the screen. And I'm going to point my thumb in the direction of the induced current. So it's going towards the right. Sorry, induced field. It's going towards the right. My fingers will naturally curl in the direction of the current. They're coming out of the coil at the top. They're going into the coil at the bottom. So they're sweeping round in the direction of this arrow here. And that's Lenz's law. In the right-hand picture, now I'm going to switch that coil off. So while it was on, there was no induced current. It was only the moment I switched it on. Now I'm going to switch it off. And again, at that moment, there's an induced EMF, an induced current. And what direction is that? Well, look, now we're taking away, we're removing a magnetic field that was going towards the left. Look at the sketch in the middle. The field lines were going towards the left through the coil. Now they've gone away. So we want to replace them. The induced magnetic field will try and replace them. It will oppose the change. So it will be a magnetic field towards the left. And so again, you can find out the direction of the current from that magnetic field, that induced magnetic field with your right hand rule. I mean, I don't know why I feel the need to demonstrate my right hand, but with the right hand rule, I'm going to point my thumb in the direction of the induced field. So now that's towards the left. My fingers, they're curling out at the bottom of the coil and back into the page at the top of the coil. They create this current in the opposite direction. Look, the two changes when you switch on and switch off, the two changes in flux are opposite one another. One, the field appears, flux appears. One, the field disappears, the flux disappears. The induced fields, therefore, are in the opposite directions because you're trying to replace, in one case, the field, and in the other case, counteract the field. And so the currents are in opposite directions. That's why the currents are in opposite directions. And that's what we saw on, remember the three demonstrations? And especially the demonstration where I had the two solenoids. When you switch it on and switch it off, the needle deflected in the opposite directions. The electromotive forces were in the opposite senses. The electrical currents, induced currents, were in opposite senses. Is that okay, Lenz's law? I'll just sit here for a moment, see if anything's in chat. Okay, so let me end with a quick example of Faraday's law. Look, I'll be frank here. I am aware that not everybody that's taking this class is planning to be a physics major. Maybe you're inclined towards medicine or dentistry or physical therapy or something else in the health sciences. That might be a possibility. There's a device, if you go into medicine, there's a device called transcranial magnetic simulation. So what is that? It's a device based on Faraday's law of induction. So it's a device used to kind of restart your neurons in a certain region of the brain, to kickstart your neurons in a region of your brain. So it's a device that creates an electrical signal, pulse, in that region of the brain to restart the neurons because they're kind of electrical devices. And it's a device that now you can't go in and stick leads inside your brain or whatever. I mean, I guess you could, but that would be kind of invasive. With Faraday's law of induction, we can induce an EMF in the brain to kickstart the neurons by putting your head in a magnetic field, putting your entire body in a magnetic field probably, and changing the magnetic field, switching it on and off. That induces EMFs, induces currents inside your brain that can kickstart, restart neurons. And so that's transcranial magnetic simulation. So here's an example of it. There's a device, one of these devices that creates a 1.5, I've lost the one here, 1.5 Tesla field. You can switch it on or switch it off in just over a tenth of a second, 120 milliseconds. And we're asked to calculate the induced EMF around a loop. This will be inside your brain, right? Due to switching off the on or off this magnetic field. And we're asked to calculate that EMF around this little 1.6 millimeter radius loop. So let's figure that out. So this induced EMF will happen when you turn the field on or turn the field off. Let's not worry about whether we turn it on and off, which determines the direction or the sense of the induced current, induced EMF. Let's just worry about the size. So firstly, we need to figure out the time rate of change of the flux. So that means we need the flux. So that means we need the magnetic field. So we've got to go through change. So we've got to go through a few steps here. The magnetic field change is 1.5 Teslas. The area of the 1.6 millimeter radius loop is 8 times 10 to the minus 6 square meters. That change in magnetic field creates a changing magnetic flux. The flux is the change in field times the area. That comes out to be 1.2 times 10 to the minus 5 Webers. That change in flux happens in 120 milliseconds, 0.12 seconds. And so we can then, with Faraday's law, calculate the induced EMF. We could also calculate an induced current. Its magnitude is the time rate of change of the magnetic flux. The change in the magnetic flux was 1.2 times 10 to the minus 5 Webers. The change in it took 0.12 seconds to occur. It gives us this voltage here. This is the little voltage that we induce, fraction of a millivolt, but that can be used to re-energize, to kickstart neurons in the brain. So this is an application in medical physics that is used to help patients. Let me end there. Just quickly summarize, and I've gone over by a couple of minutes. We introduced induction. We talked about the phenomena of induction. We explained that. We introduced magnetic flux. We explained what that meant. And then we talked about the law of induction, Faraday's, Lenz's law of induction, and examples of that.